Hello everyone, this is Kyle Welch with RCR Wireless News. I want to thank everyone for attending today's webinar, Trends in Telecom Power, presented by GE. Our presenter today is Paul Smith, Technical Marketing Manager at GE. At this time, I'd like to pass the presentation over to Paul.
Thank you, Carl. My name is Paul Smith. I'm Technical Marketing Manager for GE's Critical Power Division. And this afternoon, we're going to take a look at trends in telecom power. And we're going to take a look at some of the history and try and use an understanding of those trends to look into the future and see what direction telecom power may be taking. If you request a copy of this presentation, you'll see this abstract, which gives you kind of an overview of what we're going to do, but I'm not going to go through that as part of this presentation. I like to look at some of the history of central office switching and telecom applications, and when I do that, it kind of reminds me of the old TV show that showed up on PBS a number of years ago, Upstairs, Downstairs. And the similarities here are that in the upstairs part of this building, this is where the money is. This is where the hoi polloi live. And the analogy here is that the revenue-producing equipment, the switching office, is in the upstairs part of the building. Meanwhile, downstairs, in the servants' quarters, power equipment is toiling away to keep the upstairs equipment running, and obviously to keep revenue being generated. Taking a look back at the brief timeline of the telephone in particular, a very brief history. The telephone invention is usually accredited to Alexander Graham Bell, who was granted a patent for his work in 1876. So this is kind of usually seen as the invention of the telephone date. And as this new technology became accepted by the general public, people wanted telephones in their houses. Manual switching systems were used to route calls. You remember people asking for a particular number, and the operator in the central office would plug in a cable in a switchboard to route that call from one subscriber to another. Interesting to note in a little bit of research I did here that it was widely publicized that after a while, boy operators were replaced by more accurate and reliable girl operators. And the history is there, and the picture shows a line of ladies sitting at a switchboard. And around in the 1950s, switchboards began to be replaced by electromechanical switching systems. A lot of these were made by Western Electric, and they were based on mechanical movements, relays, and electromagnetic switches that were activated by pulses from a rotary dial telephone. Many of you may not remember rotary dial telephones, but that's what I grew up with for sure. This was the first way of providing automatic call routing. If you've ever been in one of these central offices, and I grew up visiting them with my father, who was a telephone engineer, they were very, very noisy. And in fact, the dial on telephone was artificially slowed so that the switching could keep up with the pulses that it was sending. But they did work, and they've dramatically reduced the need for operators, whether it be boys or girls. To keep everything running, and we'll talk a little bit more about the expectations, typically the central office would have 4 to 8 hours of battery backup, and in some cases there would be generators to provide for even longer outages in power. In the 80s, we began to see electronic switches. The Western Electric 5ES was almost ubiquitous. There were several other designs as well, but many of us remember the 5ESS. Minimal moving parts. These were solid-state devices. Much improved reliability, much improved speed. Now the system was able to respond to your telephone dialing as fast as you could hit the buttons. Now we're beginning to see packets and data come into the picture. And now there was a minimal need for operators. Battery backup, again, still in the 4 to 8 hour time frame. And now in the 21st century, we're looking at central office switching systems really morphing into data centers. And the central office is becoming filled with server racks. We're seeing computerized call routing. Voice signals are almost all digital. Data, bandwidth, and speed are the buzzwords of the day. And many of the features and functions of the telephone system are software defined, so that they can add features very easily. And you'll hear now, what is an operator? People nowadays don't know what an operator is all about. And some of the requirements for backup are being reduced, and we'll look a little bit at why that may be. Quality of service and expectations. Expectations have changed, and they're still changing. Expectations are different for different applications, and we'll look a little bit at some of those applications. Used to be with telephone service, plain old telephone service, dial tone was the expectation. And the typical subscriber would say, when I pick up the telephone, there should always be a dial tone. And this was whether or not his lights were on, he still expected that there would be a dial tone. The implications of that were that the telephone should be powered not by the electricity from the home, but in fact by electricity sent from the central office. And for that reason, 4 to 8 hours of battery backup were provided in the central office so that the telephone would always work. And longer backups were provided by generators. Another application, internet access, and again, the expectation here is probably a search engine, or at least your home page. Criteria is when I open my browser, the Google page appears, or whatever your home page is set to be. The implications of that, that a short delay may be acceptable, rerouted to an alternate site if necessary. Short backup is required to be able to reroute a request to a different site. And in this case, maybe a transfer that is not seamless may be acceptable. If the search results take 3 or 4 seconds to come back, that's probably acceptable. If it has to be rerouted and takes a little bit longer. And then we've got mission critical applications. These are the E911 commercial applications, banking, medical applications, where the criteria really is, I cannot afford any interruption in critical services. It's essential that if there is going to be a transfer of operations from one location to another, it be seamless. And that typically means that 2 systems have to be running the same application at the same time. There may be batteries and generators for power backup. And indeed, in some locations, in some applications, there may be a dual utility feed, so that if one utility feed goes away, there's a second one backing it up. Battery technologies to provide this power backup. The technology that's been used for years and years and years is the flooded lead acid battery. And the illustration here is some of the old Bell Labs AT&T round cells, the list 1Ss. Typical application in the central office, 10,000 amps, requirement for 8 hours of reserve, and a 48-volt system. That's looking at 80,000 ampere hours of battery reserve. With the list 1Ss, which were typically around 1,600 ampere hours, that's 50 strings, each string having 24 of those 2-volt cells that you see on those shelves. That's 500,000 pounds or 220 metric tons of battery. And they take up 3,500 square feet even when they're stacked too high. That's why they're usually in the basement, because if you put them somewhere else, they're going to end up in the basement. If we look at a requirement for 15 minutes of reserve time for the same 10,000 amp 48 volt system, now we're only looking at 2,500 ampere hours of reserve. With the list 1S's again, that's only 2 strings of 24 cells, a mere 15,625 pounds or 7 tons, but 110 square feet is considerably less too. And that's a whole lot easier to find somewhere to put it. Other technologies, VRLA, valve-regulated lead-acid batteries, the sealed lead-acid batteries, have found a way into many, many applications, even in central offices. Lots of cell sites and what have you, using VRLA batteries. Then some places are using nickel-cadmium, lithium-ion, sodium-nickel chloride, each with their own set of advantages, but at a cost, and we'll talk more about that. Battery chemistry advances. We're looking at different technologies here from the standpoint of the vertical axis, which is the weight density, and the horizontal axis is the space density, the volumetric energy density. And you can see that lead acid scores pretty low on both those scales. But when you get out to the lithium polymer, lithium ion, you can see that there's almost a 10x reduction in weight for the same amount of capacity versus the lead acid. If you look at the volume, there's almost a 10x reduction in volume. The space that's taken up by these batteries could be 10 times less. So obviously that's some fairly significant changes just from changing the chemistry of the battery. Size and weight advantages, reductions are available at a cost. And more about that in a moment. Rectifier Technologies. Rectifier is what we're using to take the utility AC to convert it to 48 volts DC. Back in the 70s, the ferro-resonant rectifier, the illustration here is a 200 amp unit, 6 foot tall, 12.5 inches by 16 inches in footprint, weighs 725 pounds. Not something that you unplug and replace should it go wrong. Switch mode rectifiers come along in the 90s, couple of generations there up to 2008, where we're looking at significant reductions in size and weight, all the way up to today's rectifier. That particular illustration is a 100 amp rectifier, so it's not a direct comparison, but if we compare two of those, it's the equivalent of the other ones shown there. So we're looking at a reduction in weight from 725 pounds down to 8.2 pounds. And the efficiency is the other thing to point out here, that the efficiency in electrical conversion of the old ferros was in the 80s percentage-wise, and that's being brought up now to 96 to 97% is very commonplace for today's rectifiers. Rectifier upgrades, we can get significant utility savings by upgrading rectifiers. And it's very easy to say, okay, well, I'll just rip out a power plant and put in the new one, and I can get my savings that way. But the cost of reconnecting all the loads to a typical power plant can be as high as the cost of the power plant itself. So the ability to unplug the old rectifiers and plug in a new, more efficient one is clearly a significant cost savings in terms of the installation costs. And the way we've done that in several cases is take one of the new rectifiers and put it into a carrier or adapter, and that allows you to plug the new rectifier into the older system. In terms of utility savings, we put together a calculator which has found quite a lot of use. And in this illustration, you can see that for a 3,500 amp power plant, with a nominal voltage of 52 volts, what we do is we specify what the legacy plant is, what the plant is that we're replacing. In this case, it was 15 400 amp ferros in terms of the capacity, calculates what the utility cost is based on the efficiency of those rectifiers and the utilization, because the efficiency changes with different utilization percentages. And then we do the same calculations for the upgraded plant, and we had several customers that wanted to be able to leave some of the old rectifiers in place. So this allows you to leave some of those in place and build a hybrid plant with new rectifiers. This illustration is replacing all of the rectifiers, but the calculator allows you to do partial replacements as well. Does the same utility calculations for the new power plant. It calculates the savings and also, for interest's sake, the annual CO2 reduction. And it's not an inconsiderable number. It also takes into account some of the building parameters. You can see here that if I improve the efficiency of the rectifiers, I generate less heat. That means my HVAC system has to work less hard. So I can have some savings, and we calculate that based on how efficient we think the HVAC system is. Similarly, it is able to calculate some approximate cost of replacement equipment based on what we're taking out and what we're replacing it with, and give you a very simple payback period. I don't like to use that number very much because it is very simplified. But typically we are seeing savings in this particular instance. The savings were $56,000, almost $57,000 a year, based on the parameters that were fed into the model. Rule of thumb, I like rules of thumb. These basically simplify things to something which we can all very easily calculate. But you can expect an annual savings of $1 for each amp of load and each 1% improvement in efficiency that you implement. And that's all based on a 10 cents per kilowatt hour utility rate. For example, a 1,000 amp load, a 10% improvement in efficiency, you can expect $10,000 per year in savings. That includes the HVAC savings. So what we're seeing here is some intersection of technologies. The battery technology, we've seen significant reductions in size and weight. We've also got rectifier technology, reductions in size and weight from the improvements in rectifier technology. And we've also got the digital technology, and this is the technology which allows for some equipment to be provided with reduced backup time, reduced battery capacity. Some equipment is still mandated by the FCC to have minimum reserve times, but in many cases, some of the newer switching equipment can in fact be provided with lower backup times. So these converge to give us the opportunity to look at some different architectural implementations of DC power plants, and what I'm calling architectural flexibility. If we look at the centralized architecture, which was typically what was used for the what I call my upstairs downstairs analogy, down in the basement you've got a large power plant, a large array of batteries, some primary DC distribution, feeding up to BDFPs, feeding loads in the upstairs revenue producing area of the central office. With a distributed architecture, we now take that power plant and we put it alongside the load equipment. And this is made possible by the reduced size of the rectifiers, by the reduced size and weight of the batteries, for all the reasons that we talked about. Reduced backup time gives us a smaller battery, smaller rectifiers, and three-phase balanced input rectifiers in many cases. Smaller capacity systems, since they're located at the end of a single row and they're only powering a single row, and because now the floor loading has a chance of maintaining this, it can now go upstairs or downstairs. This also gives us the flexibility to provide load-specific backup time. So if I have a row of equipment which only requires 15 minutes of backup, because the functionality is able to be duplicated elsewhere, or I have a way of switching to another system within 15 minutes, then I can provide only 15 minutes to that particular row of equipment. If the next row along actually requires 8 hours worth of batteries, then I can provide the batteries required by that row only. And you can see a similar sort of cabinet to the load equipment with batteries, small rectifiers, and some distribution within that single cabinet. Taking that one step further, if we can make the system smaller still, now I can put the power and the backup batteries in the bottom of each cabinet. So now I don't have a dedicated power cabinet. I have a dedicated power area within each of my load cabinets. And you can see that this gives you, with the advent of some of these small batteries, small rectifiers, again, it gives you those same abilities with the smaller loads, smaller rectifiers, smaller capacity system. Now I can provide flexibility of the backup time at the cabinet level rather than the row level. So even more flexibility in terms of the backup time provided. So this distributed architecture has some significant advantages. Efficiency. When we move DC power from one location to another at 48 volts, it requires significant size of cables because the currents are relatively high at a 48 volt DC voltage. The efficiency of the rectifier obviously helps, but if I'm putting the rectifier as close to the load as possible, then I'm not getting as much losses on the 48 volt side. The losses will come on the AC side, which typically would be at 480 volts AC, and the losses are significantly less for a given size of conductor. These all lead to lower operating expenses. And I can put the load and the power cabinet closer together, saving me money on copper cable. Because, as I mentioned, the AC cabling is much smaller gauge than the equivalent in DC cabling. Cooling, I have a reduction in cooling capacity because, or cooling needs, because I'm generating less heat from improved efficiency and decreased losses. Flexible energy reserve. This is my ability to provide only the reserve that's needed by the particular equipment. I don't have to provide 8 hours for the entire facility. I can now provide only what each piece of equipment actually needs. Reliability. If I break down my user group into smaller chunks, then my reliability is actually improved, providing that I've got the appropriate redundancy strategy both within the power system and also within the overall telecommunications system. Scalability. I only add power when I add load. I don't have to build a ginormous power plant just for a single cabinet. I have to add a cabinet, then I add the power. I add a row of cabinets, then I add a power cabinet, whichever way I've chosen to go. So I'm not spending all the money up front. I only add the power equipment as I need it. That reduces the upfront capex big time. So looking forward, what does this mean in terms of what we can expect going forward? As rectifiers have improved, we took the ferro rectifiers and we made the first generation of switch mode rectifiers in a much smaller space. We had to put fans in them because we had to move air through to dissipate the heat generated within the rectifier to prevent it from overheating. As we've made rectifiers more efficient, there is less heat generated within the rectifier itself. We'll reach a point very soon where the efficiency of the rectifier is high enough that we don't need the fan to move air through to get rid of the heat. This in itself will add another layer of improved efficiency because the fan consumes some power itself. So not having a fan will inherently make the rectifier more efficient. It will also make it more reliable. One of the first things to fail in today's switch mode rectifiers is typically the fan, and in some cases they're user replaceable. But as costs have come down, that's less and less the case. Looking forward, power conversion closer to the load, improving overall efficiency. I think we're going to see more of this. We're going to go from distributing the power to the end of the row to distributing it to within the cabinet. Reduces the operating costs. Batteries closer to the load. This reduces losses. It also allows you to use more of the energy from the battery. So not only do you need, in some cases, smaller reserve times, but you can get the same reserve time from a slightly smaller battery because you're not incurring so much losses from the battery to the load. We're also looking, I think, for power conversion direct from 3-phase 480 volts AC to probably down to 12 volts directly into the load. In some cases, the servers are looking for 12 volts, and a lot of times that's done by one of these silver box power supplies from 110 or 220 volts. But if we can feed them directly from 3-phase 480 volts, then our AC losses are reduced. We remove a conversion step from the end-to-end powertrain, so we can actually reduce losses because of the reduced number of conversion steps. It also inherently maintains three-phase balance if you have a true three-phase rectifier feeding the load. What this does is allows you to make sure that your UPS or other backup system is balanced from the standpoint of phase-to-phase loading. In a lot of data centers, phase balancing is done manually. You have to remember when you add a load which phase of the AC you're going to add it to. So being able to do automatic phase balancing takes a lot of the manual effort out of adding loads. So it simplifies significantly the loading of your source. So in summary, expectations have changed and certainly are different for different applications, and we saw that with the different applications that we looked at. Reserve times may be significantly lower. Some of these are mandated by the FCC, but if we can reduce reserve times, we reduce the number of batteries and give ourselves a lot more flexibility in where we can put power plants. Reduced reserve time reduces the size of the battery, both through the requirements and also through providing options in terms of different chemistries. Rectifier size is reduced. That's allowed us to put rectifiers in places where we previously couldn't put them. Size and weight reduction also allows us to put them in places where they previously wouldn't go. And really, all of these combine to enable this distributed power architecture. The distributed architecture improves the end-to-end efficiency. It also adds flexibility, scalability. It reduces copper usage and also the losses involved in copper, reducing capital expenditure and improving operating expenses. The future offers more of the same with even greater efficiency, reduced numbers of power conversion steps, and more flexibility in terms of being able to keep equipment running for less cost. And that's the end of the formal presentation. We will look at some questions now, if there have been questions, and see what feedback we've got.
All right, Paul. Yeah, thank you for that presentation. We've had a number of questions come in, so we'll just jump right in. So the first one, to take advantage of increased efficiency, Are you able to replace other manufacturers' rectifiers with retrofit kits?
Yes, that's an interesting comment and question. We've had a number of applications where we've been asked to replace some of these old ferro rectifiers with new systems. And in fact, the ferro rectifiers were all connected together to a single bus bar. And we've been able to replace numerous different manufacturers' rectifiers with small cabinets of switch mode rectifiers. Which really are optimized to reduce the installation cost, like we talked about. It's very easy to take out a complete system and add a new system, but if you can minimize the installation cost, that's a significant benefit. And yes, it's not limited to one manufacturer in terms of rectifiers. In the case of the plug-in rectifiers, it's a little more difficult to make something that's universal, but in many cases it is possible with those two.
Great. Next question we had come in is, why are three-phase rectifiers more efficient?
Three-phase rectifiers are not necessarily inherently more efficient. I'm sorry if I gave that impression. A three-phase rectifier is as efficient. What we found is that inherently more efficient comes from the higher input voltage. In other words, a 480 volt input voltage will yield an inherently more efficient rectifier than a 240 volt input rectifier. Really, the other efficiency comes from the losses which are involved in the conductors. The higher the voltage, the lower the current, and the lower the losses in a given conductor. This really is why people are looking at high voltage DC in some applications for the same reason. And whilst that does give you similar reductions in losses, it does introduce some other issues. And I'm not sure that the reduction in losses is any better in high voltage DC than it is with 480 volts AC. But really, the improved efficiency comes from the reduction in conversion steps and the reduction in the current in the conductors.
Very great. And a good follow-up question we had actually come in is, with rectifiers that you have replaced with more efficient ones, how much of an efficiency improvement have you demonstrated?
Well, in the case of replacing some of the switch mode rectifiers, the older units were 88 to 90% efficient, some 91, 92%. But we're replacing those with 96 to 97% efficient units. So we're seeing at least 6 to 7% improvement in efficiency in direct substitution of switch mode rectifiers. In the case of the older ferros, where we've seen some units that were as low as 82%, you may be looking at 15% improvement in efficiency, and that's quite dramatic. With all these rectifiers, the efficiency varies a little bit with its utilization, and also with the age of the rectifier. Unless a ferro rectifier has been properly maintained, its efficiency will in fact decrease over time. So as it ages, it may be considerably less efficient than it was when it was first installed.
Great. Next question we had come in is, what sort of cost differential is there between lead acid and some of these other denser chemistries?
That varies with the chemistry, but at least a 2 to 3 times factor in most cases. In the case of the sodium battery, it may be as much as 5 times the cost. What you have to remember is that in a lot of cases, you're justifying the additional cost by some other offsetting factor, such as space requirement. We had one customer where we used the sodium batteries because the alternative was to build a bigger building or move to a bigger building, and the cost of that is obviously prohibitive. We were able to remove a section of his lead acid batteries and replace them by sodium batteries, which, even though they were 5 times more expensive, avoided the cost of having to expand his building or move to another building. So in those cases, they're actually a much cheaper solution, even though the cost of the batteries themselves may be 2 to 5 times more.
Okay, great. So we had another question come in about three-phase rectifiers. So are there any cost savings generated by three-phase rectifiers because of the phase balance?
There's a couple of things to look at with phase balance. One is the cost of the utility power. In some cases where phases are not balanced, the utility may have a surcharge for the power that you're using from the utility. So there can be some hidden costs in not keeping the phases balanced. The second is the capacity. If you're using a three-phase, and most large facilities are using a three-phase UPS, if you don't apply your load to the three phases uniformly, the UPS may start telling you that you're running out of capacity, whereas in fact you've got plenty of capacity on 2 out of 3 of the phases. You're just running out of capacity on the one that's getting loaded up most. So there are some cost effects based on potentially having to upgrade the UPS prematurely. Similarly, there are costs involved in manually doing the alternative, which is to plug the loads into the right phase and make sure that they're plugged into phases in a balanced and even manner. So there are costs involved as well as the in other parts of the rectifier itself.
Okay, great. Looks like we have time for about one more question. So in a distributed architecture, how much extra battery capacity do you typically have to supply as compared to a centralized architecture?
I think this question comes from the fact that if you divide up your battery reserve into smaller chunks, you're going to end up with maybe more than you started with in a centralized system. And certainly, if all other factors are equivalent, then that can happen. That there would be a 5 to 10% increase in battery capacity over the centralized system. But what we have to look at here is that that's offset, more than offset in most cases, by the fact that you've now got reserve time flexibility, which means that you don't have to provide the full 8 hours or 4 hours for every piece of equipment. So you can reduce the battery capacity on many of your pieces of equipment in the modern facility, and the flexibility of the distributed architecture allows you to do that. So in most of the examples that we've looked at, the battery capacity actually ends up being significantly less, not more.
Okay, great. That's about all the time we have today. I want to thank everyone for attending today's webinar, Trends in Telecom Power, presented by GE. Again, our presenter today was Paul Smith, Technical Marketing Manager at GE. Thank you, Paul.
Thank you, everybody.